to the cloud. It goes. Okay.
Okay. Yeah, so this is the first UMA Academy session that Melissa and I have been talking about. We want to just record a series of educational presentations about our technology and the blockchain technology in general. Originally, this was meant to be for internal education, so everyone would get on the same page about how the claimed app is going to work, how we're going to distribute the KPI options, and then that way we could all be on the same page in terms of discussing design trade-offs. But we figured learning about Merkle trees is pretty fundamental to knowing about blockchain. So we figured, like, why not just do a short presentation on how they work and how they're being used in the wild today. So this will be a short, last time was around 30, 40 minutes, a little Q&A after. Cool. All right, so to contextualize this presentation, we're going to talk about Merkle trees. We're going to discuss how they work and how are they used in practice by other blockchain technologies, and also just other tech companies in general. We're going to talk about what a hash function is, which is underlying the Merkle tree data structure. Cool. So the first topic is, what is a hash function? I'm not sure how much everyone knows about hash functions, but they are underlying all the blockchain technology today. So a hash function is a one-way algorithm. It's some sort of mathematical relationship where you pass in the input and you pass it through the hash function, and it returns you a fixed size of some seemingly random series of bits. And this is called the hash value. What's really cool about hash functions is you can pass in any size data. So you can pass in a single word fox, you can pass in a book, you can pass in an image through this hash function, and it will always return a hash value that looks the exact same. It's the same length, but it's just seemingly random. To understand the hash function, we just think about its properties. So the properties are the 5 properties I listed here. It's deterministic, meaning that anytime you pass the same input into the hash function, you're always getting the same hash value. It's really, really hard to reverse a hash value. So if you take a look at the graphic on the right, it's really easy to go left to right. It's really, really hard to go right to left. And when I say really, really hard, I mean that you either need a lot of computing power, so some of the most powerful computers in the world and probably running them at the same time, or you need a lot of the time. So you need thousands of years. So it's basically infeasible to reverse a hash value. A hash function is collision resistant. Yep.
Nick, can I just interrupt there? I think there's a really good way to think about the difficulty of this. It's actually, first of all, like, even with all the computing power on the earth, you wouldn't be able to like reverse a hash function without knowing the input easily, especially if the output is large enough, like if it's 256 bits, which is what's typically used. The other thing I'll say is that, like, the best way, the good hash functions today, the best way people know how to reverse it is just to guess inputs, right? So you just like guess until you get the right one. And nobody really has any other better ways to find a good hash function. No one has any better way to find the input other than just guessing inputs, which means basically you have to guess like a huge number of times, like 2 to the 256, which is like a number of molecules, or sorry, number of atoms in the universe. So it's like just it's completely infeasible to reverse good hash functions. Now some hash functions get broken, but generally the idea is it's completely infeasible and basically impossible.
Yep. So it's really hard to break a hash function. Hash functions are collision resistant, which means that any 2 inputs should never map to the same output. If you do, then you can create all sort of security problems where a lot of apps rely on a correct hash value being presented. But if the same hash value maps to 2 different inputs, that app can be confused about which input it's being passed. The avalanche effect, if you change one tiny bit of the input, it creates an avalanche in the hash value, as in the bottom two example inputs in the graphic, the red fox runs and the red fox walks, those two, even though they look very similar on the input side, they should be very different on the hash value side. And hash speed. So the hashing itself should be pretty fast. So the main advantage of a hash function is that huge amounts of data can be squashed together into this hash function and can be identified solely through their hash value. So I can hash together a giant book. I can get a single like 256-bit hash value and pass it to someone else, and then they can theoretically verify that it came from the original book with no changes.
So I just want to mention one other thing here. One really helpful metaphor for a hash function is fingerprinting. It's a lot of people actually refer to it as fingerprinting the data. So you can't generate the original data from the hash function, or sorry, from the hash. Obviously, you can't reverse it. But if you were given that input, you could verify it. So you could basically, if you're just like with a fingerprint, if you have the person, if you just see a fingerprint, you can't say that maps to this person. But if you have a person in the police station, you can fingerprint them and be like, yep, that matches this fingerprint. I know this was the same person.
Yeah, that's a really good segue into this slide where hashing, one of the first applications of hashing was to make sure email was valid. Back when email was one of the main applications on the web, people wanted to verify that emails were being sent by the correct sender. So what someone could do is someone could say, send an email to someone, and then also pass to the receiver their public key. And this way the receiver would be able to verify that the email was hashed with the public key that they own. This specific example is you can verify that an email has no altered links, like no links that produce viruses, by passing the original hash value. So that's the original hash digest in this image, where the original contents of the email, including all hyperlinks, hash to that hash digest. And if some attacker tried to intercept your email and inject a bad link on the way to you, you could verify that this altered email would produce a different hash digest. Another example of hashing is used whenever you download files. A lot of websites will present you a button to click that says download, but as savvy web users know, you shouldn't just blindly click these buttons. Usually these sites will offer you some sort of hash value or a public key and a hash digest. And what they'll do is they'll say, when you download your file, you should hash the file contents against our own public key. And you can verify that the downloaded file has not changed on the way from the website to you, which is possible if you're downloading on an unsecure server. Here's an example of Ledger Live. Ledger Live, for example, offers you the SHA-512 sum hash, which is just the hash of this specific SHA-512 hash function. And this way you can verify that the Ledger Live version that you're downloading is the correct Ledger Live version. So in summary, a hash function allows you to hash any set of arbitrary data to produce a hash value. The hash value is only recoverable if you have the original set of data. And even the smallest change to one set of that data will produce a completely different hash value. So it's a way to verify data. And this leads us into Merkle trees. Merkle trees are otherwise known as hash trees. And it's fundamentally a tree data structure, but it has an interesting property where each non-leaf node, we'll go into that in the next slide, is a hash of its child nodes.
Yeah, that's a quick question.
Yep.
On hash functions. So underlying loss of encryption in some sense is hash functions, right? You know, you want to, a password is hashed, assaulted, and it's encrypted, correct? So as you stated, the solving for these problems, like actually reverse engineering, an output is really difficult. But why does quantum computing often break some of these standard encryptions that we use?
For one, you can just you can run a lot of computations in parallel on quantum relative to normal computers. So you basically you get more speed. So you can remove the time constraint.
And it's significantly reduced, yeah?
Yeah, exactly. Like it's still performing the dumb checking yes method, but it's just doing a lot faster.
Right. So it has to brute force it, but it could do so like magnitudes faster. So therefore
Exactly.
it doesn't take, the heat death of the universe. It takes, a week or something.
Yeah, exactly. Yep.
Yeah, I would also want to mention that like the problems, there are only a certain subset of problems that quantum computers can solve. So some encryption algorithms specifically are quantum computing resistant and some are not. And this is because like quantum computers have a particular method of, like we said, like trying a lot of things in at the same time, kind of. It's actually, I don't understand the details of exactly what types of algorithms work and which ones don't, but effectively you're using quantum properties to basically try things all at once, right? Like literally try them all at once using these quantum properties. And so, but certain algorithms you can do that with and certain algorithms you cannot. From what I understand, I do not believe most common hash functions can be broken or reversed by quantum computers. I don't believe that's true. I think it's pretty much only encryption algorithms specifically. And I believe Ethereum and Bitcoin encryption algorithms are not quantum resistant, but I think that they have proposed moving to ones that are. So it's a solvable problem, I believe.
Interesting.
Yeah,
Yep.
actually in the new hard fork to Berlin, they had some release notes about switching some of the underlying algorithms towards quantum resistant algorithms. I forget what they're used for. They're not like the core algorithms, but there are parts of Ethereum that are not quantum resistant.
Cool. Thank you. Thank you.
It's actually whatever the BLS, I'm not sure what that is. I think that's not quantum resistant, and they're thinking about changing that. Okay, so Merkle trees. So the Merkle tree, a really simple Merkle tree is the image on the left. And the definition of a Merkle tree is each non-leaf node. So any node in this tree that's not at the bottom, the bottom nodes are called leaves. So that's L1 through L4, those are leaves. Everything else is a hash of its respective child nodes. And the child nodes are the nodes below a node. So think of the data blocks L1 through L4. You can think of them as symboling balances. So L1 say is my balance, and L2 is your balance, and L3 is someone else's, and so on and so on. And this Merkle tree is a collection of our balances. So it represents the state of some environment. So it's best to understand a Merkle tree just by building it from the ground up, and then we'll think about some of the cool properties we can get once we construct it. So like before, data 0 through data 3 are, these are just arbitrary data blocks, and these are the leaves of our tree. So we're going to create the first set of nodes for the Merkle tree, and we're going to simply hash each of the data blocks. So nodes 0 through 3 are just the hashes of the corresponding leaves. Then we're gonna add another part to the tree. These are going to be parents of the children 0 through 3. So node 4, symbolized by the number on the top left, is the hash of its two children 0 and 1. And node 5 is the hash of 2 and 3. And so on and so on, and you go forth and you finally get to a single node at the top. And this is called the root node or the root hash. So what's pretty interesting about this Merkle tree is that, first of all, we're using the hash function throughout. Every time we're creating a node from the bottom up, we're hashing data. So we're either hashing the leaf data or we're hashing nodes themselves. So therefore, if we were to modify data 1, then every node above it would be its hash value would change. So if we were to modify data 1, then the hash of 1 would change, and therefore the hash of 4 would change, and then the root hash would change. Same with data 2, which would affect the hash of node 2 and the hash of node 5 and up to the root. So what's pretty interesting about the Merkle tree is that we can actually store the entire state of the Merkle tree just by storing the root hash. As long as the root hash does not change, then you can be confident that all of the leaf nodes have not changed. So this is an interesting property used in blockchains where you don't, if a blockchain wants to store a ton of state, if it's storing that state within a Merkle tree, it doesn't actually have to store each individual node. It only has to store the root node to prove that none of the data has changed. Another interesting property is that we can prove that any of the nodes belong to the tree, assuming that we have the root node and we also pass in data from all the nodes on the path from the root to the leaf. So if we want to prove that data 0 is in this tree, then we need to pass it its parent node, the parent of that parent node and its sibling and its other children to get its hash, and then up to the root. But you don't, to prove data 0 belongs in the tree, you don't need anything on the right side of the tree. And this is because we can back out, we can make a relationship between data 0 and the root without touching the right side of the tree, just based on how we constructed the tree originally.
So if I understand what you're saying correctly, Nick, you're saying that you only need 1 and 5 to prove that data 0 is part of the tree. Is that correct?
Yes, that's correct.
Okay, cool.
Yeah.
So like you only need 2 pieces of information to prove that data 0 is in the tree, which is like way smaller than like the 4 pieces of data that are in the tree, and that like relationship gets exponentially better as the tree gets bigger. So if you had like 1,000 nodes, you might only need, a very small number, maybe on the order of like 10 or so piece of information to prove that you're in the tree.
Okay, so now we can talk about what are the 3 benefits of Merkle trees, and we sort of touched on these already. Number 1 is you can store lots of data really easily. So no matter how large the tree is, i.e., no matter how many leaves are in the tree, you only need to store the root. And so say if we're talking about an application that's very storage intensive, like the blockchain, then if we want to store an entire Merkle tree on the blockchain, all we have to do is store the root hash. If you want to prove that any node is in a tree, you need relatively very few of the nodes within the tree to prove membership. And finally, tamper resistance. If you want to verify that the tree state is how you think it is, all you need to do is compare that tree's root hash to the root hash you think, and if they're different, then the trees are different. So actually, the Bitcoin blockchain is really simplistically, it's a linked list of blocks where each block has a single root hash, and that root hash represents the entire state of Bitcoin, and each block represents the proposed or updated Merkle tree with all of the updated balances. So say we're at block 0 today, and there's a certain root hash. If in the next block I send a transaction to someone else, then that's going to ripple through the entire tree. It's going to update the root hash, and then I will add that updated root hash to the next block. So Merkle trees in practice they can store state like blockchains. Bitcoin and Ethereum both use Merkle trees. Ethereum uses a derivative of a Merkle tree. It actually uses 3 different Merkle trees, each of which store different data about the EVM state because it wants to achieve Turing completeness. But at the root of Ethereum is still the Merkle tree concept. Any other applications that store a lot of state like Git or IPFS, they often use Merkle trees because, again, all they need to do is remember the history of Merkle root hashes instead of storing the entire tree. So one of the cool case studies of a Merkle tree is it's really good to store an entire list on chain. So Uniswap recently airdropped Uni to hundreds of thousands of users. And the really simplistic way of implementing this would be to store an 100,000 length array on Ethereum and update every single claimant's balance to claim. And then any claimer could go to their dApp and claim their specific balance. But this would have been incredibly expensive for Uni to initialize that array in the first place. So what Uniswap did is Uniswap stored all of their claims in a Merkle tree off-chain. So they created a list of 100,000 claims and they put that into a Merkle tree. And then they derived the Merkle root hash from that. And they uploaded that Merkle root hash to a smart contract. And then what any user could have done is any user could have proved that their claim is within this Merkle tree, going back to the previous proving hash or proving logic here. They could have proved relatively efficiently that their specific claim lies within the Uniswap Merkle tree. And this allowed Uniswap to efficiently upload all of the claims on chain, and it allowed users to relatively efficiently claim their data. And the Uniswap dApp, if anyone here has claimed their Uni, what you were doing when you click that button, claim Uni, what you were doing is essentially submitting a Merkle proof that your claim was within the tree. What Uniswap did one step further to make the claim even more efficient was Uniswap pre-computed every single claim's proof for every single user and stored all of those proofs on IPFS. So what the dApp did was, when a user submitted their claim on the dApp would then retrieve their corresponding proof from an IPFS database and then submit that proof to the smart contract, and the smart contract would be able to easily verify that proof proved that the claimant is within the tree. And then the Uniswap, yep.
Weren't the I think the pre-computed proofs were stored on Cloudflare, right? Not IPFS, right?
Yeah. I think that's right. I'm actually
yeah. So I think the full Merkle tree was stored on IPFS. I think the pre-computed proofs were stored on Cloudflare. But I mean, it's roughly the same thing. But yeah, Cloudflare is like, they stored on Cloudflare to make the access a little bit easier and faster. But whatever. Yeah.
Good catch. Good catch. So I don't know if this comes across very clearly, but I was able to go, so their Merkle tree for the original Uniswap allocations is still online. And you can see that merkle.uniswap.org. Don't click on it because it's a really, really large database. It's like 100,000, it's an 100,000 long key set with, and each one of the entries has a lot of data in it. And it like almost bricked my computer when I clicked on it. But I was able to grab a little bit of data from it. And I was able to grab actually the first few claims, which are pretty interesting. So if you can see, also let me know if the text is too small in the image on the right. But so the first claim, you'll see it's for the address 0x000. The second claim is for 0x001. The next one's for 0x leet, and the next one's for 0x dead. And they all had claims. They claimed a certain amount, which is written in hexadecimal in this example, and the proof is available. And then there was some extra metadata. So like, is the user a SOX owner, or were they a liquidity provider on Uniswap, or were just they a Uniswap user? These are all different reasons why people got the original Uniswap allocations, but that's sort of extra and not really relevant to the claim smart contract. But all of this, so imagine that a giant dictionary of claims is hosted on the website. What the dApp did was it detected your claimer address, and it fetched this proof from this website, and it submitted that proof into the smart contract, and the smart contract was able to essentially check off that your claim happened, and then it sent you Uni. Balancer also uses a slightly derived version of Uniswap smart contract, whereas Uniswap deployed a one-time Merkle tree. So they deployed a single contract and they uploaded a single root hash for all 100,000 uni claims. And once it was deployed, it was never used for anything else. Now, Balancer wanted to distribute claims in consecutive weeks. So every week, Balancer gives away rewards, and they wanted to reuse the same contract for all of that. So what Balancer does is Balancer modified their smart contract to store an array or a mapping of Merkle roots. So every week, the Balancer team uploads a new Merkle root with that week's allocations, and users can then sort of go through a similar process of submitting a proof and claiming for that week. And finally, we get to UMA's Merkle distributor. So we are going to do, the current design is we're going to be able to store multiple distributions like Balancer. For example, we might, every week we give out liquidity mining, dev mining, KPI options, and every one of these lists is going to be its own Merkle tree. And we also allow each individual distribution, so each Merkle tree, to specify what reward token is being paid out on. And that's going to be specified in the smart contract. So say in week 0, the foundation is going to upload 1,000 UMA or 1,000 KPI options, and it's going to upload a list of all claimants. It's going to create a Merkle root from there and deploy that Merkle root to the smart contract, and then users are going to be able to claim for that week. Cool, and that's it. That's the Merkle tree. I'm curious, does anyone have any questions, discussion, anything?
It's like random ones. So the first transaction from Uniswap, that's from the null. Isn't that from the null address, the 0x000? Isn't that like no one owns that? So someone just burned a bunch of uni? Is that what that transaction actually means?
Possibly. If you look at the flags in that claim, it's true for isLP and true for isUser. So somehow the 0x0 address was both an LP and a user of Uniswap. I don't know. Matt, do you have any idea?
No. I'm wondering, like, is there some way that you could trick? I wonder how they're actually generating these events. I wonder if there's like a way that you could trick Uniswap into thinking that. How many tokens did they get?
I don't know.
Like a lot?
0x1. We have to put that into hex.
Yeah, yeah, because as far as I understand, no one actually owns that address, right? Like it has.
Yep.
Yeah, that's where you literally, people send if they're burning their tokens, that's where they send
Well,
it.
you probably could have sent your LP tokens to that address, and then it would be able to get some from LPing theoretically.
I wonder if it's a test, but I think anyone can claim for anyone else. So like, it's kind of weird because that means that somebody could just basically burn uni tokens.
Yeah, but it was also like, it was also
Oh.
free for them to basically burn uni tokens. Like at the time, it was not worth anything,
Yeah.
and this is the first distribution, so I'm sure it's just almost like a joke or a gag or something.
Maybe.
Like they sent tokens to Leap, like 1 through 37. I don't know who owns that address, but
Oh, did they
I don't know
really?
if it's, yeah. Look at the 4 claims: zero address. The next one is a 1 address. The next one is 1 through 37, and the next one is DEAD.
Yeah, those are definitely not real. Like those are too hard to find. Nobody would be
Yeah.
able to actually. Nobody has the keys for those. Interesting. Weird. Unless somebody like did some weird, like somehow tricked Uniswap into thinking that those are. Wait, those are LPs and they're socks? No, they're not socks.
0x0 is LP and the user. I don't think Uni got tricked. I think, first of all, I think that these are ordered like on purpose. Like I imagine these are, it's not a coincidence that these are the first ones listed.
So it makes sense that they're LPs, right? Like my guess is people have burned LP tokens accidentally or
Yeah.
purposefully, like sent them to 0x0 before or 0x1.
Yeah,
Yeah,
one
according according to Etherscan, 0x0 has like $902 million worth of tokens.
Like
Yeah.
900 million.
Yeah, because that's where people
Liquid.
burn stuff. Like that's how
Yeah.
contracts like
Mhm.
provably burn things.
Exactly. Yeah,
Kind
because
of amazing.
if anyone actually had the key to that, they would just transfer it all out and they would be filthy, filthy, filthy rich.
Yeah.
Well, I think the funny thing is like they also probably wouldn't be able to do anything because most things in the ecosystem use 0x0 as like the you
Yeah.
sent an incorrect address. So you probably wouldn't be able to transfer a token in the first place.
Yeah, I'm pretty
Right.
sure that's set as like an unusable address.
Or I guess you could transfer the ether though, but maybe you couldn't transfer the maybe you couldn't transfer ERC20 tokens.
Yeah,
Is
I mean, it
there-
depends on the token implementation, I guess, technically, but it would be fascinating. You can actually play around with this because, like, on a mainnet fork, if you do this in Ganache, you can do like a mainnet fork and then pretend that you're some address. You can even pretend you're like a contract or pretend you're any address. You can make Ganache like unlock that address, and you can actually try making calls from 0x0 and see what happens.
Interesting.
So,
Well, that's
might be a
probably
fun
what,
experiment.
I mean, that's probably how it became a user. Like people maybe submitted a transaction from it.
Well, no, you can't actually submit a real transaction. You can only do it
Ah.
on a fork because, like, you need on a fork you can do it without signing, but on mainnet you couldn't do that.
My other
Yeah,
guess
I don't know
is
how
that
you can
all,
force. Oh, go
on
ahead.
their side, my other guess is that all LPs are users, but not all users are LPs.
Ooh, that could be it. That could be it. Yeah. Or maybe like if you do, I wonder if like you do I think you can do trades where you like input from one address and then output to a different address. Like you like send through Uniswap. And I wonder if
Mhm.
both of those addresses are considered users, because if you sent 0x0 as the output address, then that could make 0x0 a user. Anyway,
Hmm.
it'd be cool to like to try to like I'm sure you could actually figure this out by like going and looking at their scripts to generate these
I wonder if
setups.
someone's claimed for the zero address yet. That's also like
Yeah.
not just eyeballing it. That's probably a lot of tokens.
It could be. Yeah.
It's like a long hex number.
It could be like an intentional burn of Uniswap. I don't know how they would they. I've never used it, but you wonder if they had a posted why they might have done this themselves, right?
We got to get you using Uniswap, Jason. Going to be part of your workflow.
Yeah, cool concept. Gas prices are insane. That's why I typically have not done decentralized transfers personally.
Nope, you're right. But it'll get better. Faith, hope is on the horizon. Nick, this thing was really awesome. Thank you for putting this together. It's really cool.
Yeah, hopefully it was somewhat educational, and yeah, it's going to be saved for prosperity or posterity.
Both.